Hello, this is our third of 3 videos for section 3.5. We're talking about transformations here. We've gone through the horizontal and the vertical shifts. We've talked about the horizontal and vertical compressions and stretches. So this is our final types of transformations, and we are using the reflections about the x-axis and the y-axis. So it's not that bad. I think the compressions and the stretches are a little bit more complicated than these, but these can cause problems if there are a lot of compound issues on a lot of transformations that are being applied at the same time. So what is this? When the right side of a function, y equals fx, is multiplied by -1, the graph of the new function, y equals negative f of x, is reflected about the x-axis of the graph y equals f of x. I just call it turned upside down. So if the graph is turned upside down, that's what it does. Okay? Now, when the graph of the y equals f of x is known, the graph of the new function y equals f of negative x is reflected about the y-axis of the graph of the function y equals f of x. Okay? So one is reflected about the x-axis, one is reflected about the y-axis. The difference is where the negative is placed. If the negative is placed on the outside, it's a vertical reflection. If it's a negative that's placed on the inside, it's going to be reflected about the y-axis. Okay? So we know what the square root function looks like, right? It looks like that a little shape that starts at the origin and goes this way. Okay? So if we have a negative on the outside, negative square root of x, that graph is going to be turned upside down. It's going to be taken upside down. It's going to be vertically reflected across the x-axis. If the negative is on the inside, like a square root of a negative x, it's going to be reflected across the y-axis, and it's going to be facing the other direction. Okay? We'll talk a little bit more about that when we need to. So, alrighty? Alright, so graph the function f of x equals negative x squared, and then also find the domain and the range. Okay? So we already know what that graph looks like, right? It's the parabola shape. Alright. So we begin with the graph of y equals x squared as shown in black in figure 56. And here it comes. There it is. For each point xy on the graph of y equals x squared, the point x negative y, because you're taking the opposite of all the y coordinates. And that gives us, that's going to be found in table 13. So again, I keep saying this. We don't really do this table all the time. We're trying to minimize this one, but it's for instructional purposes, if nothing else. It's showing you what's going on. So when you're on the exam, I would prefer actually not to see the table. Okay, so because you're going to want to just turn the thing upside down. So if you have y equals x squared, that's the same table, and then you take the opposite of it. And so those respective values are opposites of what you started with. What that comes out is a graph that's turned upside down. So the black graph is the y equals x squared, and the blue graph is f of x equals negative x squared. It's turned upside down. It's reflected across the x-axis. And what's the domain? Now we're talking about the blue graph, right? We're on the blue one. So the domain is all real numbers. Now what's the range? On the blue one, the high point is at it touches the x-axis, but it then goes down. So the range is 0 and below. Another way to say that is negative infinity to 0. So negative infinity to 0, and you do include the 0. Okay? So this is now going to be a reflection across the y-axis. Now we talked about this a second ago, right? I said, what happens when it's the square root of a negative x? It goes in that direction. So find the domain, the range while we're at it. Okay. So to get the values of f of x equals the square root of a negative x, you begin with the graph of y equals the square root of x. And we're going to see that in our figure 57. For each point xy on the graph, y equals the square root of x, the point negative xy is on it. So on the graph of y equals negative square root of x. Square root of a negative x. And then we obtain that graph by reflecting the graph of the black graph, y equals square root of x, about the y-axis. So there's the illustration on this figure. So the square root of x looks like that, right? Now, if you're ever in doubt of why this is happening, because a lot of people see that blue graph and they're thinking, wait, I thought you cannot take the square root of negative numbers, and if you're to the left of the origin, you got negative numbers over there. So that's why it confuses a lot of people when you're dealing with the square root of x and it's going that direction. You got to remember though, it's y equals negative square root of x, right? Sorry, square root of a negative x, the square root of a negative x. So when you place the negative 4 back in, you're going to get the 2 because you're taking the square root of a negative 4. See, the inputs on the blue is already negative. So the blue has negative inputs. And so if you take the square root of a negative x, you're taking the opposite of what's given to you. Well, they're given to you negative 4, negative 1, negative 9. They're given to you those numbers. So when you put those negative numbers back into the original function, square root of a negative x, it's going to take the opposite, allowing you to take the square root of positive numbers. So putting in a negative 1, you end up taking the square root of a positive 1 because you're taking the opposite of it. So that's why the graph is facing that direction. Alrighty? So what's the domain? Okay, it's everything to the left of 0, so it's negative infinity to 0. It's another one of those cases what I was telling you about. The domain is not always all real numbers. Okay, this is when you have a starting point and going in one direction. So it's negative infinity to 0, and the range obviously is above the x-axis, so it's 0 to infinity. All right? All right. Now, this one is one that's really complicated, okay? We're going to combine graph procedures, okay? So we're going to graph the f of x equals 2 over x plus 2 minus 1. Now, first of all, there's a couple issues at hand here, okay? What is the parent function? Well, it's not absolute value of x, is it? No. Which one did we have that had the x in the bottom? Wasn't the reciprocal function 1 over x? That butterfly I referred to when we talked about that video? It was the one that was a butterfly on it. Okay, so what I'm going to do is I'm going to rearrange the terms slightly. So it's going to be helpful to write it as 2 times 1 over x plus 2 minus 1. Now some of these transformations we can recognize already. The 2 out front is going to stretch it, right? The minus 1 that's all the way to the right, that's going to bring the graph down 1 unit, right? Yeah. And then what is the 1 over x plus 2? Well, it's going to take that 1 over x, remember, graph, whatever that one is, the 1 over x graph, and move it 2 units to the left. And I think that's what our steps was saying. So you begin with your 1 over x, and then the doubling to 2 times 1 over x, which is 2 over x, that's going to stretch it by a factor of 2. So our wicked butterfly, the wings are going to be a lot steeper, okay? And then you're going to take that graph and move it 2 units to the left. That's a horizontal shift. And then finally the minus 1 will drop those wings 1 unit below. Like I said, this one is, you earn your stripes on this one. If you can get this one right, you earn your stripes. Alrighty? So let's look at the graph. We begin with the y equals 1 over x. That's our first one. That's our parent. Okay? Then we double it. So the wings are just stretched out. So take some key points on the graph, 1, 1, and move it to 1, 2. Go from 2, 1/2 to 2, 1. So it's stretched out a little bit. Then what's our next one? Well, now we're at 2 over x. Now we're going to take that one and apply the x plus 2. So that pushes the graph horizontally to the left 2 units. Now notice that little blue dotted line right there. That is called a vertical asymptote. And the reason it's called a vertical asymptote is because negative 2 is not in the domain. When you move that graph 2 units to the left, there is a boundary there that can't be crossed because that negative 2, you can't put that into the function. So before when the butterflies was hovering across that y-axis, that vertical asymptote was kind of covered up. But when you moved it 2 units to the left, you have to show me that it doesn't cross that point. it's kind of illustrated that on the original graph when it's doing that y-axis. But when you move it 2 units to the left, you get to show the vertical asymptote. Okay, so that's when you move it 2 units to the left. Now what's left? We got to take that graph and move it 1 unit down. So now there's our y equals 2 over x plus 2. And now we're going to take that graph and move it 1 unit down. But for the same reasoning, it was hugging the x-axis. Now it's going to be hugging another line right below that at -1. Whoops, sorry. Okay, so that's what the graph is going to look like. All right. So, oh, by the way, what is the domain here? The domain is all real numbers except for what? -2, because there's a vertical asymptote. But here's where it's kind of tough. What's the range? Well, you see the arrows go up and you see the arrows go down, so you start thinking, oh, it's all real numbers then. But there is one y-coordinate that the graph never hits. And that's right, and that's the y equals -1. So the domain is all real numbers except for -2, because it can't cross the x-axis, it can't cross that dotted vertical line. And so it's all real numbers except for -2, and the range is all real numbers except for -1, because that's the y-coordinates. All right? All right. So now the transformation of a square root function, y, now I put these all under one slide here, try to see if I can combine them here. So f of x equals the square root of 1 minus x plus 2. So we begin with the square root of x, right? All right, so that's what the square root of x looks like. And then we're going to take that negative x, square root of a negative x, because the f of x has a negative x inside there. So that one is going to turn it 1 unit to the left. Sorry, not 1 unit to the left. It shifts it going the other direction, because we did that a while ago. The square root of a negative x made it go the other direction. And then what do? Okay, we take that graph and we're going to have to move it 1 unit to the right. Because if you kind of try to manipulate that, that's going to be the square root of negative x minus 1. And then make it go 1 unit to the right. Alrighty, so then the only thing left to do now is apply the plus 2 to it, but that's a vertical shift. So it's kind of like cut and paste, cut and paste, cut and paste. Okay, so take the first graph, flip it, and then paste it to the next one, 1 unit to the right, and then 2 units up. So the final graph is the final result. It's the square root of 1 minus x plus 2. But notice I was able to do this without a single table of plotting points. And that's where we want to be. That's what we want to do. So you got to take one step at a time, though. If you don't know anything about transformations, and you're faced with graphing the square root of 1 minus x plus 2, you had no idea what the parent function is about, square root of x, just what square root of x does in the first place, all you could possibly do here is just graph this function by plotting several dozens of points, and hopefully get enough points to get it in the right position. Way too much time. You wouldn't even finish a test if you don't know the transformations here. Plotting points, just doing that is not enough. So you got to know, what does the negative do to it. First of all, you got to know what the square root of x looks like. And you got to know what the parent function is. So you got to know what the square root of x looks like in the first place. And that's the very first one up there. And then you got to know what the negative does to it. Oh, it makes it go the other direction. And then how does that 1 fit in? Well, it'll make it go to the right with a little bit of algebra there. And then what does the plus 2 to it? Oh, that makes that graph go up 2 units. So it's kind of like a recipe. You do this, then you do this, you do this, you do that. And so you finally get to the final answer. It may say, well, it still takes a while to do that way. Yeah, it is, but it's a lot better than plotting points. And if that's all you had at your disposal. Okay? So that concludes the vertical the vertical reflections and the horizontal reflections. When you reflect something across the x-axis and you reflect something across the y-axis. And we also talked about here a lot of the transformations being put together. So these last couple examples, we were actually doing multiple transformations here. We were doing horizontal vertical shifts. We were doing horizontal vertical reflections. And so they're all put together here. And so, all right. So as you're doing these, I am sure you're going to have questions. And I am sure you really need to ask those questions, and we'll put them in the student request videos. And again, the author has lots of videos pertaining to these things as well. And then if you can give some questions to me, we can put it on a student request video slide in MyMathLab, and we can build that library as well. And so if other students have some of the same questions that you might be having, it helps everybody. So, and as always, you have a good day.